Okay, so you guys have some sheet on your table. So the first question, I want you guys to define what is Le Chatelier principle. And the second question is, how does equilibrium constant dictate your concentration? Okay, so just answer these two questions on your sheet. So if you're not sure how to answer the second question, you can list out a simple equation like A plus B equal to C, and then you can use that equation to express how does the K will control the concentration. Think about when you adding a reagent or remove a product, how does the K have a role in the equilibrium? If you haven't finished writing a sentence, you can continue working on it, but I'm going to start what we'll be talking about today. So last time we talked about the dissociation of acetic acid, which is a common ingredient in vinegar, that would dissociate when you add water, but importantly, it's only partially dissociated into acetate ion and the corresponding hydronium ion, right? So this is the concentration of this H3O plus would be your pH. It will indicate how acidic this solution could be. Okay, so if we write our equation, your Ka of product over reactant and excluding water since it is a liquid, then you rearrange the Ka expression and you can get this equation. So the importance of this equation tell you about the relations between the concentration and the equilibrium constant for acid. Okay, so if we look at this term, then you can imagine if we add a strong acid to the system, the Le Chatelier principle is going to make this equation or chemical expression to shift backward, shift the equilibrium position backward, right? Because for an equilibrated system, the concentrations are fixed. These are controlled by thermodynamics, and we'll go into it later. And that's why I want you guys to think about what does the Le Chatelier principle indicate. Okay, so if we add more strong acid, the equilibrium shifts backward. Okay, so that means you have more of these acetic acid, right? So that means your final pH is going to go up. So then we'll get back to this in a little bit when we talk about buffer solution. All right, so last lecture I talked about KSP, and I noticed that I made a mistake saying KSP stands for solubility parameter. So actually that is not parameter, it's solubility product. Okay, so solubility parameter is something else. Okay, so when you see KSP, usually when we're talking about dissolution, our starting material is a solid. In another sense, when we refer to precipitation, we consider how many ions will combine and form a solid. So it really depends on how you write the expression to describe your chemical system. So for solubility product, typically it has an equation like this. Okay, because once the solid is formed, it's not in your system anymore. It's a precipitate. So when you write your expression, that terms go away. So you generally look at what is dissolved. So previously, in the previous lectures, we remember you can find K, the equilibrium constant, from pressure and concentration, correct? Everybody remember that? So the relation between these, for KSP, generally we don't talk about pressure because it's something is dissolved in liquids. So we only care about concentration, okay? And then these are simply the factor that balance your stoichiometry. And then when we're talking about KSP, we generally do not consider the partially dissociated or associated ions, okay? Because for simplification, inorganic and in analytical chemistry, you guys will run into issues where you will form something, they are somewhat connected, okay, but they're not fully dissociated, okay, and that will change your equilibrium because that means you have multiple equilibrium going on. But when we're talking about equilibrium, we're referring to a state that's at infinite time when everything reaches the equilibrium and there's no more change in concentration, okay? So why is KSP important? Because this term can describe solubility, but it's not a very precise description of solubility, okay? Because we forget about the non-dissociated or somewhat dissociated species that are present in solution. Okay, so a great example is if we're talking about the dissolution of lead chloride. What I mean by partially dissociated is forming something like this, and then its counter ion would likely to be a hydroxide, okay? And then in the next lecture we'll go into complex ions, and they're indeed complex, okay? So we do not care about the formation of this when we're talking about KSP. We only care about fully dissociated ions that are solvated by our water molecules. So if you have your book, you can go to appendix A13. It's near the end of the book. So you will see a table, a very big table of KSP values. Now I want you guys to get into groups to consider cation size, okay, and consider the anion size, and to see if you can find any trends. So actually, there's no trend in these solubility product, okay? So because each of them is really case by case, okay? So generally, you would figure it out. You'll be able to, for certain anion, for a fixed anion, you can see there are certain metals that tend to precipitate and certain metals tend to not precipitate, okay? So this has to do with how well these ions can be solvated, okay? Because we haven't talked about thermodynamics, so it's hard to explain this at the point. But generally, there are some classic examples such as silver chloride, right? But I want you to notice the order of magnitude. So for example, if you look at chloride, silver chloride is 10 to the negative 10, okay? So the smaller the KSP is, the less soluble it is, because we're looking at it going from solid to ionized form. How can we get solubility from KSP? Let's look at one example of lead fluoride. Let's say by experiment, we figured out the solubility of lead fluoride is this much. So try to calculate KSP from this value. Now get into group. So you can look up the molecular weight. I mean, you don't have to get a very precise molecular weight for lead and fluoride, but you can just get an approximation. So let's see. Lead will be, so you can say fluorine is 19. Okay, let's do a quick calculation. So first you write down what KSP equal to. Look at this unit. Most chemists will work with mole per liter. So you know what to do here, right? You get the formula weight, you can convert this to mole per liter, right? So if you do the math, you will get this. So how does one can determine solubility? So generally, we'll make a saturated solution, right? And then we can filter out what is not soluble and evaporate our solvent, and then we can figure it out what's the actual solubility. So typically, people would do it in triplicate. I mean, do it 3 times so you get an average value of solubility. Once you convert the gram per liter to mole, right? Then we can write out an expression for KSP. So don't forget this factor here. Okay, so the tricky part for these calculations is a lot of time people would get, okay, well let's see, this one would dissociate into lead and fluoride, right? So then they say, okay, well these two concentrations are the same. So immediately, a lot of you would get some answer like this. Is that right or wrong? Is that reasonable? So actually, we have to recognize that whenever you have multiple ions that dissociate, 1 molar of this actually produce 1 molar of lead and 2 molar of fluoride. So do not get tricked by an expression like this. Okay, so a proper way to write this should be, okay, make sense? Right, you need to increase this factor because whenever 1 molar of this dissolves, you make 2 molar of fluoride ions. That's why you need to double the concentration of fluoride. And then the square is come from this KSP expression. So now we will do a practice problem that you can calculate solubility from KSP. So we know from the book, let's work backward. Try to calculate solubility from the KSP value. Does anyone have problem with doing this calculation? Raise your hand, I can come to your table. So you should be able to write down the expression for KSP with the ion that's formed. How many of you get this? Then we know, this is the tricky part, okay? You have to recognize each of the calcium hydroxide will produce 2 hydroxide ions, right? So we can set this, say, the solubility, okay, well, it only produces 1 calcium ion, right? So we can set this to S. Then this term, because you're producing double amount of calcium ion that you have, 2S, but don't forget the square. Then you solve for S. You equal these two equations together. You solve for S. Then you should be able to get the solubility of calcium hydroxide. No, so no, actually this is a mole, right? So that means it's lead fluoride is dissolved. And the calcium hydroxide, if you look at the KSP, right? So a lot of time you see this type of order of magnitude, you do not have a sense of it. But if you put it into the context, if you remember, okay, so calcium hydroxide, we know that's something that's not that soluble in water that have 10 to the negative 6. If you have something like the previous one would be, I didn't write it out, but it would be on the order of 10 to the negative 8, negative 9, right? So we know that lead fluoride is much less soluble than calcium hydroxide. In another example, let's look at the common component in our bone. Our bone are made of a mixture of mineral and some soft tissues, right? The main component of a mineral is calcium phosphate. So if you remember from last semester, we have some reading assignment about your teeth, okay? And how this can react with acid, then that causes the erosion of your teeth, okay? So calcium phosphate, when you're doing calculation for calcium phosphate, I want you to list out the KSP expression in terms of the ion that's formed from calcium phosphate, this equation in terms of solubility. So you would get, because you're forming 3 times of this calcium phosphate molecule, and then don't forget the factor up here, and then for here you're getting 2 molecules of phosphate and square. Then if you can look up the A13 table, you can find the calcium phosphate solubility, KSP, is on the order of negative 29. Does this make sense to you? It's on a 10 to the negative 29, right? So it's very small value. So it makes sense, right? Otherwise your teeth would dissolve away. Your bone would dissolve away in the presence of water if it is a very soluble, like for example, sodium chloride, right? It would dissolve immediately in water. So the reason why I do these practices is you have to be careful when you are doing your calculations, and you will be likely run into such calculation later on in your life, okay? More advanced chemistry course will look at KSP and look at how does other factor will influence it. And for today, we will only talk about one effect, which is the common ion effect, okay? So let's look at this calcium hydroxide example. What would happen if we add more strong base to this system, such as sodium hydroxide and potassium hydroxide? we would expect it to dissociate completely and then generate more hydroxide, correct? So once more hydroxide are added to the system, it's going to shift the equilibrium to the starting material, which is the precipitate, which is a solid, right? So we'll decrease the solubility in the presence of a common ion, okay? So in this case, it's a base, all right? So in another example, if we're looking at another thing that is not very soluble, that is commonly used as an imaging agent, barium sulfate, okay? So if we're adding a lot of sodium sulfate, we know sodium sulfate, they have very good solubility. It's similar to the strong base. How would you make a sodium sulfate? It will be from a strong acid and a strong base. So that means they like to dissociate completely, because the hydroxide and the hydronium, they just combine and form water. So if we look at its KSP, it's about 10 to the negative 10. And we know it forms 1 molar of each. So we can figure it out. Our concentration of sulfate would be about 10 to the negative 5. So what would happen if we put barium sulfate in 0.1 molar sodium sulfate? Okay, so 0.1 molar sodium sulfate is going to give you 0.1 molar of the sulfate ions. If we look at the order of magnitude, this is 10 to the negative 1. This is 10 to the negative 5. So if we go back to the expression, at the equilibrium, it's supposed to only get to 10 to the negative 5 for barium sulfate to dissolve or dissociate completely. But in 0.1 molar of sodium sulfate, this value becomes so big. So that means it's going to shift the equilibrium backward, okay, due to the Le Chatelier principle. Obviously, we can recalculate its solubility. So our solubility is limited by KSP value, right? So in the case where you have about 10 to the negative 1 of sulfate, what the concentration would be for barium ion. So this is dictated by KSP, right? So equilibrium constant. So that means your barium ion concentration would be about 10 to the negative 9, because this is the absolute constant. Okay, these are changeable. Okay, chemical systems are dynamic. Once you change one part of it, or you perturb the system, I mean you change the concentration of your starting material or your product, you're going to shift the equilibrium position, okay, but your equilibrium remains constant unless you change the temperature. All right, so what does this mean? In the 0.1 molar sodium sulfate solution, barium sulfate is less soluble than that of, in the case that it's dissolved in pure water. So after discussing about the common ion effect, if we put more sulfuric acid to the system, what will happen? Let's say 0.1 molar. How many of you think the same thing will happen as this case? So it will be exactly the same case. This again, strong acid associate completely. Okay, so in the system, it prefer to reach to this equilibrium constant. So these two are the same case. Okay, so this leads to the next concept. It's called the pH effect. Okay, so when we're talking about pH, we're talking about the amount of a hydronium ion is present in the system. Okay, so if we're adding acid to the following compound, what will happen? Please discuss with your partner about how does the solubility of these compounds will change when you add acid. It's either increase or decrease, or doesn't change, right? So if you finish these three, I want you guys to consider these cases. So it may be helpful if you can write out the expression of what happened to these ions, these salt, okay, when they dissociate completely. Okay, so how many of you think this will increase the solubility? If we imagine we have calcium and fluoride present in the solution, right? And we know HF is a weak acid, right? So that means as controlled by the Ka value of HF, it's more of a covalent compound, right? So the fluoride ion will immediately go grab the hydronium ion or the proton that's present in solution, right? So the fact that you're adding acid to the system, you're removing fluoride from your system. You're making the associated or solvated fluoride ion becoming HF. But the amount of it is very small, of course. But anyway, based on, as suggested by KSP, if you're removing fluoride, more of these will dissolve because it wants to increase the calcium, the fluoride concentration and calcium concentration so that it reaches equilibrium. So similarly, as you may guess, if you add acid to this, okay, of course there will be an acid-base reaction. So your acid is neutralizing the hydroxide. And of course, the solubility is increased because you're generating water, right? Again, you're removing hydroxide ions. But in this case, we know HI is a strong acid. It's not going to do anything because the iodide doesn't have affinity for the added proton to the system. Okay, let's look at this system. HCN, is it a strong acid or a weak acid? If you're not sure, look up your Ka table. I think in the earlier chapter, I didn't look it up, but HCN, we know it's a weak acid, right? So we can get the similar result. So it's going to increase your HCN. And again, so for the HCl, it's a strong acid, nothing will happen. So now this is a tricky one. Talk to your partner about this. What will happen to a phosphate? So if we look at phosphate, and last lecture we talked about the multiple equilibrium, right? The phosphoric acid is going to turn into multiple pKa, right? As you go down, the Ka becomes smaller and smaller. So we know Kw is equal to Ka times Kb, right? So if you become less acidic, that means you're somewhat becoming more basic. So by using this concept, we know phosphate is slightly basic. It wants to become, okay, I did not put the charge here. It wants to become one of these ions. Okay, so as dictated by Ka, it will want to take that proton away, right? So once it becomes this species, it's no longer the phosphate. And that's why when I said when we're talking about these solubility product, we have an oversimplification is we do not consider these intermediate ions. So again, this, once you add acid, it's gonna take away your phosphate and then you're gonna shift the equilibrium. So in this case, it's also increase. So previously we talked about we can use Q to describe our system that is not at equilibrium. So again, if we think about QSP, okay, it's larger than K, and QSP is less than K. Let's look at this case. When the QSP is larger than K, what will happen? If we think about when you list out equation, your Q will equal to something like this, right? So if this value, the product of this is larger than this, what will happen? The equilibrium is going to shift backward to the solid form, right? So that leads to precipitation. So this is precipitation. And for QSP less than K, it will be dissolution. Because your concentration hasn't reached to the equilibrium yet. That means more of these solid will dissolve. So these are very important concepts. All right, now we'll briefly touch on buffer. So I know I'll give back the experiment observation, and I'm happy to see several of you recognize the fact that we mix acetic acid and sodium acetate, it makes a buffer. Okay, so what is a buffer? So buffer generally is made with a weak acid and its conjugated base, or a weak base and its conjugate acid. So it's in the equilibrium. So A buffer solution means within a certain concentration of acid, or strong base is added, the pH remain unaffected. Okay, that's why we call it a buffer. Our biological system are mostly a buffer solution. Your pH, your blood pH doesn't change unless you have some disease. Okay, so similar to these cases here, when you add more acid to a weak acid, it's gonna consume that added acid, the added proton to the system. So there's one important equation in the buffer world is this Henderson-Hasselbalch equation that would describe how does the concentration of your acid and your conjugate base affect the final pH and how that related to pKa. Okay, so I guess the definition for buffer is that it's the strength or the ability of a solution to maintain its pH in the presence of added strong acid and strong base. So native log is essentially pH, right? So this is your pKa term. And then we can, for the ease of this equation, okay, so this is generally the final form of this Henderson-Hasselbalch equation. Okay, so we know when this ratio of these is equal to 1, log 1, the answer is 0, right? So when this is equal to 1, so they are balanced, this term can go away because that equal to 0. So at that point, your pH equal to pKa. So in a natural or a perfect scenario where you add a weak acid directly to your system, you're going to get a pH equal to pKa. We can adding additional amount of anion, which would be sodium acetate or potassium acetate, doesn't really matter under dilute condition. And in general chemistry, we will only talk about dilute condition. So later on in analytical chemistry, when you're dealing with a solution with high amount of salt, they're not completely dissociated. So these simplified view of how does added anion or added cation would affect your solution pH would not be true. Okay, so I think that's all for today.